Hello again. We are back with Chapter 11, Infinite Sequences and Series. This is Section 11.9, Representations of Functions as Power Series. We studied last time what it means for a power series to converge, and if it does converge, it's going to converge to a function, f of x, and that function's domain is going to be the values of x for which that series will converge if you substitute those values of x into the series, turning it into a numerical series. We are looking first at the geometric power series. We can take a look at the infinite sum from n equals 0 to infinity of x to the n, and looking at that expression, we see that a here is equal to 1 and r here is equal to x. So as long as the absolute value of r is less than 1, in other words, as long as the absolute value of x is less than 1, then we will have a convergent series, and it's a convergent geometric series, and we see that it would converge to a over 1 minus r as the sum. And if we plug that value, those values of a and r into the equation, we can see that our geometric power series converges to 1 over 1 minus x, and the interval of convergence will be minus 1 to 1, where the negative 1 and 1 are not included. So now we're going to play around geometrically or algebraically with other expressions and use this fact so that we can find power series representations for other functions. So let's take a look at f of x equal to 1 over 1 plus 2 times x. So I'm actually going to make that look like a 1 over 1 minus by using some algebra facts. So I can say and rewrite this expression as 1 over 1 minus negative 2x, right? That's certainly equivalent. And now that I have the negative 2x as my new quote-unquote value of x, I can actually substitute that into an infinite sum notation from n equals 0 to infinity, and now my new power function has base negative 2x. This is not considered a correct power function form. We do want an expression c sub n to be our coefficients of our power series, and then we want a base power function. So we want either x to the n or an x minus a to the n. So I'm going to continue simplifying this to put it in proper power function form by doing some more algebra manipulations. And I can use my power rules or exponent rules and say that this is negative 2 to the n times x to the n. I could theoretically leave it as just that, or you could go even further and say that this is equal to minus 1 to the n times 2 to the n times x to the n. And this expression in here is our c sub n, right? So we would have a c sub n times x to the n, and this is our proper power series form, and this is a power series representation for the function 1 over 1 plus 2x. Because we are using the geometric series to find an expression for 1 over 1 plus 2x, we know that as long as the absolute value of r is less than 1, we will have convergence, right? So we want to substitute our value in here and say as long as negative 2x absolute value is less than 1, and if I solve for x here, I would get less than 1/2. And because we are dealing with a geometric series, we know that our endpoints will not converge, so we do not need to test our endpoints here, and we would say that our interval of convergence is going to be negative 1/2 comma 1/2 open interval. All right, so let's play with this one. More algebra is in order, and I'm first going to split up my numerator and denominator into a product of expressions So that's going to equal 3x squared times 1 over 8 minus x cubed. I want 1 over 1 minus an expression in x. I don't want 1 over 8 minus something. So now I'm going to manipulate a little bit more by factoring out that 8. So this is going to equal 3x squared over 8 times 1 minus x cubed divided by 8. That's certainly true. And I can even go one step further to make it clear that this is 3x squared over 8 times 1 over 1 minus, and put my x cubed over 8 in parentheses. So far so good. Now that I have a 1 over 1 minus an x expression, I can use that x to the n infinite summation. So if I just come here and say that this is equal to 3x squared over 8 times the infinite sum from n equals 0 to infinity of an expression in n, and I'm going to substitute that value, x cubed over 8. Good. And whatever I had here is what I put here in my x to the n. Now I still want to manipulate this expression to be in terms of a proper power series form. So I'm going to play around with the interior, and I can see that this is going to equal 3x squared over 8 times n equal to 0, and I can pull out the 1 over 8 to the n, and I can see that this is going to be x to the 3n, because I'm just going to multiply 3 times n to distribute that n exponent. This is in proper power series form, but I still want to deal with the expression on the outside of the summation notation, and I can actually put them inside. So this is equal to the sum from n equals 0 to infinity of 3 over 8 to the n plus 1, because I'm adding another factor of 8, and I'm also adding 2 factors of x, so I would have x to the 3n plus 2. If I were to multiply x squared times x to the 3n, it would be x to the 3n plus 2. And this is my power series representation. And what is my interval of convergence? My interval of convergence is going to be the case when absolute value of r is less than 1. So I would have when x cubed over 8 is less than 1, and I would have x cubed less than 8 here, and taking the cube root, I'd have when x here is less than 2, which is the cube root of 8. So my interval of convergence here is going to be -2 to 2. Good. And this is my power series representation. So we want to be able to play with geometric series in that way. And what other techniques can we use to find power series representations of other functions? This is a very powerful theorem. And let's read that. So if a power series c sub n times x minus a to the n has a radius of convergence r that's bigger than 0, then the function defined by that power series is differentiable and therefore continuous on the interval of convergence minus the endpoints. And we could actually take the derivative of that function by taking the derivative of each of the terms of the series. So notice from here to here, what would the derivative of the term c sub n times x minus a to the n, what is the derivative with respect to x? C sub n is just an expression in n, so if we were to take a derivative there, it would be a constant, so we're not taking a derivative c sub n. But x minus a to the n, we would be taking the exponent down times a, or times x minus a, and then we would be subtracting 1, right? and then we multiply by the derivative of the inside, but the derivative of the inside is 1. So notice that we are taking the derivative term by term. Similarly, in part 2 of this theorem, we can take the integral of f of x, and we would be taking the integral of each term of the series. And if I went from here to here, how would I take the integral of c sub n times x minus a to the n? I would add 1 to the exponent and divide by that exponent. So you can see, and then add plus c, that arbitrary constant. Okay, good. So given that, find a power series representation for f of x. What is the radius of convergence? And notice back also from this theorem, the radius of convergence of the power series in part 1 and part 2 is going to be the same as the original function, just the radius of convergence. It didn't say anything about the endpoints. So you will inherit the same radius of the same interval of convergence, but maybe not necessarily the endpoints. You'd have to go back and test the endpoints for convergence. All right, so I notice here, if I take my g of x equal to 1 over 1 minus x, if I rewrite that as 1 minus x to the negative 1, I notice here that the derivative of my function is going to be minus 1 times 1 minus x to the negative 2, but then times the derivative of the inside, and this ends up being a negative times a negative is a positive, and if I move my negative exponent down to the denominator, I get 1 over 1 minus x squared, which is my f of x. So I do see that 1 over 1 minus x does equal n equals 0 to infinity of x to the n, and we do know that r here is equal to 1, our radius of convergence. And so if I take a 1 over 1 minus x squared, that's going to be equal to the derivative with respect to x of 1 over 1 minus x, and that's going to be the derivative with respect to x of my summation, or my infinite sum, x to the n, and I'm going to take that term by term, and that's just going to be n equals 0 to infinity, and I'm going to take the derivative of x to the n, and that derivative is going to be n times x to the n minus 1. So I have that 1 over 1 minus x squared is going to be the infinite sum of n times x to the n minus 1, and my radius of convergence is still going to be 1. Good. All right. I can do that again. Notice again, if I had g of x equal to 1 over 1 minus x squared, that's going to be 1 minus x to the negative 2. And if I take the derivative here, I would end up with negative 2 times 1 minus x to the minus 3. And that's going to give me minus 2 over 1 minus x cubed, right? I only want 1 over, so this is going to equal negative 2 times my f of x, right? So my f of x is going to be negative 1/2 of the g prime. Good. So if I want to find my, from above, g of x is going to equal n equals 0 to infinity of n times x to the n minus 1 from a above. And so my g prime of x is going to equal n equals 0 to infinity. N is a constant, so it's just a coefficient. And so it would be n times n minus 1 times x to the n minus 1, which is minus 2. Good. But we know that our f of x, or this g prime of x, is equal to negative 2 times f of x, right? So we want our f of x, which is equal to 1 over 1 minus x cubed, is going to equal negative 1/2 times g of x, and that g of x has the infinite sum of n times n minus 1 times x to the n minus 2, and I can put that negative coefficient inside my summation, and I would get n equals 0 to infinity of minus n times n minus 1 over 2 times x to the negative 2, and that's going to give my power series representation for 1 over 1 minus x cubed. And because I started with r equal to 1, I still end up with my radius of convergence equal to 1. Good. Part C here, I have ln of 1 plus x. So I do note that the integral of 1 over 1 plus x dx does equal the ln of 1 plus x plus c, right? I also know that 1 over 1 plus x is equal to 1 over 1 minus x, and if I use the geometric series representation, I can substitute my value of negative x in here and say that, and simplify to proper power series form and get minus 1 to the n times x to the n for 1 over 1 plus x. So now if I want to take the integral with respect to dx, I would want to take the integral of my series with respect to x, and now I'm going to integrate term by term and end up with a sum n equals 0 to infinity of minus 1 to the n, and x is the variable here, so x is the one that is integrated, and it's x to a number, so we add 1 to the exponent and divide by that exponent, and then we also add c. Good. And we know from here this integral is the ln of 1 plus x. Now you might see in the table of integrals when we go to the next section that we change our index of integration. So if I wanted to change this to n equal to 1, then I would subtract 1 here from n. So I could change this to say that the ln of 1 plus x is going from 1 to infinity of minus 1, and wherever n appears, I'm going to subtract 1, because we still want to start with 0. And then we would have x to the n minus 1 plus 1 just goes to the n, and n minus 1 plus 1 just goes to the n. And you will see that that is how they represent ln of 1 plus x. They start with 1. We also note that since r up here was equal to 1, our radius of convergence down here is going to equal 1. All right, so finally we have inverse tangent of x. We do note that if y is equal to the inverse tangent of x, then y prime is 1 over 1 plus x squared. So let's play with 1, and we also know that the integral of 1 over 1 plus x squared dx is going to be equal to the inverse tangent of x plus c. So I'm going to come up with a power series representation for 1 over 1 plus x squared, and then I'm going to integrate it to get to inverse tangent of x. And that's what I do. Okay, so if I play with 1 over 1 plus x squared, that's going to give me 1 over 1 minus x squared. And from our geometric power series, we go from n equals 0 to infinity of minus x squared to the n. And I want to simplify that to proper power series form. Oops. And so I'm going to factor out the negative 1, and that's going to be minus 1 to the n, and I'm going to distribute the x squared to the nth power is going to be x to the 2n, right? And now if I go to take the integral with respect to x, then I'm going to get the inverse tangent of x, and that means I'm going to take the integral of this series n equals 0 to infinity of minus 1 to the n x to the 2n, all integrated with respect to x. And so I integrate term by term, and this is going to equal the sum of minus 1 to the n times x to the 2n plus 1, and then divided by 2n plus 1. And of course, it's an indefinite integral, so you would want to do plus c. But this is a power series representation for inverse tangent, and it's making use of that very important theorem that I can represent a power series by taking the derivative or integral of another function's known series. And because our original function had interval of convergence equal to 1, this radius of convergence is also going to equal 1. Good. All right. I will do these two examples in another section when we go to applications of